So it's my pleasure to introduce Professor Irfan Essa. Irfan is a professor in the School of Interactive Computing of the College of Computing, Georgia Tech of Georgia Tech. Georgia Tech is the only second two universities which have College of Computing in addition to Carnegie Mellon, I think.
Yep, so far.
Yes. One of the reasons is that the provost of Carnegie Mellon went to Georgia Tech's president a long time ago, I remember. So anyway, Irfan, I know him since his PhD time when Irfan did the face and other analysis by actually including RGB data and position combined and view that as a feature of each pixel. And that was then a long time ago. It's a neat idea, and it certainly did a great thing. And since then, I had an opportunity to communicate with Irfan. I always admire his neat idea and good solid theory and good implementation, and on top of that, his result is always fun to watch and has some practical value. That's exactly all of us should aim for. So with that introduction, Irfan.
Thank you, Takeo, for having me visit again. It's always fun to be back at Carnegie Mellon and visit with friends and stuff like that. And I also, as I said, I met Takeo when I was a graduate student, and he told me in my first meeting with him, you have to work hard, and I'm still trying. I'm still trying to work hard. So still trying to make progress. So with that, today I'm going to talk a little bit about some of the work that my group has been doing and and one of the themes that remains true to my work has been for a long time is I always am interested in working on video. And today we're going to talk about some of the stuff in that. First, to just get started, let's talk a little bit about the overall theme of my group. One of the things I'm interested in basically is asking questions about video in general. How can we analyze the content of video? How can we also use and enhance video, which is kind of shown here, and this is something I'll be giving you a lot more detail on today. The other thing I'm interested in is temporal analysis, and video is one great medium for this, and trying to analyze and predict what's happening in video. So activity and behavior analysis from video, and we've done this kind of stuff for sports to predict what's happening and analyze scenes like that. Another new area that I've been spending a lot of time on is trying to understand social networks and media, trying to understand if there are lots of images coming in, lots of streams coming in, can we understand more about the group itself from a more network perspective? And actually I have a lot of other new stuff happening in this space. This is again just trying to keep going into new ideas and stuff like that. Today, of course, I'm going to be concentrating more on these ideas of trying to do video analysis. And there'll be 3 different papers I'm going to talk about. Initially I was going to talk about 2, but I've just kind of added a third one because today talking to a bunch of people, it seemed like lots of people were interested in these types of things. So first idea is basically, again, how do you stabilize videos? And all of that stuff is available from the website. How do you also then do things like if you get videos like that are shaking like crazy and have rolling shutter artifacts, how do you generate from that much more stable videos? Which was actually an ICCB paper. And the third one is this kind of work of trying to figure out from videos how to segment the right kinds of superpixels for analysis. All 3 of these are actually, the first 2 are running live on YouTube. And when I say running live on YouTube, everybody says, I've got videos on YouTube too. Well, I'm going to show you today that these are actually running on YouTube. And then the third one is a web API. You can upload your videos yourself and analyze them and see what the output looks like. So if you start getting bored in this talk and you have a laptop and have videos in hand, start playing around. Sorry, didn't hit the space bar. Of course, to give credit where it's due, this work is mostly done by, and as professors like me always tell you, is these guys did the hard work and I take the credit for it. Matthias is my PhD student working with me. He's been working with Google also at the same time. Vivek Quatra is a former student of mine who's been at Google. Some of you may know him. He did some really good start work on trying to do things like graph cut textures, being able to synthesize textures from data and stuff like that. And also I used that as a formation of image synthesis and video synthesis. videos. The other two people, I think one of your students, Mehan, has been involved with some of this work, who's at Google. And this is Daniel Castro, who's actually one of my undergraduates, who's been also doing work as an intern at Google. So this work is largely stuff I'm going to talk about is work that we did at Google and Georgia Tech a little bit. And of course, to do a whole lot of this stuff, there are lots of people at YouTube involved who actually did take some of our stuff and put it on YouTube. So here is, basically this is a video shot right from YouTube. I'm not running it live right now. But you these days get a lot of videos like this. This is a video camera somebody put on their head, a GoPro, and started running. If you go to YouTube right now, you hit that one button. Count till 5, 1, 2, 3, 4, 5, and you'll get a real-time preview, which is this one. From that one, what basically we have done is stabilize that video. Stabilize is it's less shaky and more kind of just stable, per se, right? So that's what you see. And this is, as I said, running live on YouTube right now. And in fact, where's Christoph? This morning he said, oh, I want to try out rolling shutter. And I said, okay, let's try it. And we tried it when he was there, and actually looked better, I think. At least I think it looked better. So this is what I'm going to tell you how we got about to doing this kind of stuff. And as I said, if you have videos that you're capturing from your handhelds and want to try it out, please feel free to do so. Let's actually give you a little bit of more concrete examples. A large chunk of the video on YouTube or any kind of casual videos are like this, right? Captured by a handheld. And when you're capturing it, one of the things you will notice, it's really hard to keep it stable. It jumps around a little bit. So it has a low frequency shake like this, in addition to some high frequency jitters because your hand is shaky and stuff like that. And of course, there's a lot of other stuff going on. A couple of other things, and these will all kind of set up the stage of assumptions that we can make. Most of these videos are wide angle. And one of the beautiful things about video to some extent is the videographer will do their best to keep the main subject in the center whenever there is one subject. So now let's actually use those two things and some of the cinematographic aspects of that in mind. So using this video, which actually is still watchable, and I'll show you many videos that are not, we can convert it to something like this. So of course now you notice the video is cropped a little bit. The jerkiness has been removed, and bounces have been also removed. And of course, when we look at them, both of them next to each other, this is what you will see. So yes, it has been zoomed up. I did say the assumption is that it's a little bit of a wider angle shot. Now we can't really do much about the fact that this person moved the camera over there. Sometimes you will have problems like, well, yeah, the feet did, the legs did cut off a little bit. So that's one of the goals we have, and we'll try to now walk through and see how we got about it. So the goal is we want to actually do this for casual videos. I mean, professionals can put their cameras on tripods like that big one there and stabilize it and do actually a lot of good job with it. We want to be able to do this on casual handheld videos. We want to do it fully automatic, no intervention whatsoever. If you notice the video I showed you, there was one button click. That's one of the requirements that YouTube had on us when we started doing this. Robust, that it basically need to be able to work on really complicated kinds of videos, but also when it fails, it should fail gracefully, meaning that it should not explode. There should be a solution at the end. And it could actually just be the original video itself. We don't want it to kind of explode, which is actually a common phenomenon. I'll show you examples of this when you start getting into kind of 3D reconstruction from video and stuff like that. And of course, I want to be able to do real-time performance. And as I said, you saw the video streaming live at about 1/4 the video resolution after I just counted 1, 2, 3, 4, 5 seconds. Now, before we go there, yes, video stabilization has been out there for a long time. Post-process video stabilization has existed for a while too, where you can buy very expensive softwares. In fact, you can buy, and actually we'll do comparisons in the later part of this talk with videos from well-known packages like Adobe After Effects and Adobe Premiere, which actually do this quite well. But problem with those, or not problem, these are professional grade. There are lots of parameters you have to set and stuff. Of course, there are all kinds of nowadays stabilization algorithms also built onto handheld cameras. And you may notice that some of them are very good for high frequency jitter. They don't really account for the low frequency bounces and stuff like that. Of course, more importantly, these days, the world has moved entirely to handheld, and there are lots of actually video stabilization algorithms running on both the Android and iOS platforms. For those of you who are curious, if you do have your newest iOS platform camera, and you go from images to video and you hit the stabilization one, you notice it zooms in all of a sudden. Anybody notice this? Not try it out later today. What it does is basically equivalent to what I just talked about with a crop. It finds a plane within that which is much smaller, and they kind of do this. And of course, the other interesting things with this kind of stuff is they can actually use the IMU sensor within the camera to help you with some of the stabilization, and they do. Of course, remember my goal was to be able to do this on any video, irrespective of knowing anything about the camera whatsoever. So it should be anything whatsoever that's available out there. So the main steps of our approach at the first end of it is to be able to take the camera and estimate paths. I mean, this could be standard motion track scale, T types of stuff. Everybody here knows about this, because it has Kanade's name on it. And estimates the camera path from feature points like this. Of course, just to kind of lay this out, just imagine this motion over time, and this would be kind of the dominant motion path of this kind of stuff. What we want to do is we want to take this path and smooth it out. And we use and I'll give you a little bit more detail about it by doing Elvin optimization on it. Once we do this, what we want to do with that is then synthesize newer views of that kind of a location in that path. So a large part of what we want to do is take those paths that have a lot of high frequency jitters and stuff like that, predominant motion, and find the best path through it. How do we do this is basically we want to take paths like this, and again, I did say something about cinematography. In fact, one of the things we spent a lot of time thinking about this was, how would a camera really move? And of course, if we start looking at it is, if there's there's this red path, and I want to find a stable path through it. Well, let's actually look at it a little bit hard. When it was a tripod, it'll be stable like this, and there will be paths like this, straight angles through the whole trajectory. So that would be the tripod model. We basically look at it as a differential of that, and we want to try to minimize it towards 0. Another one, the second order differential, would be these types of linear changes, which would be when you would put a camera on a dolly or pan it. Dolly, pan. So these would be the kinds of motions we want to look at. And the third one would be when you do ease in and ease out, one motion to the other. Simple models, but we're looking for those in that original red path, and we want to try to figure out the best possible way of finding those small pieces, piecewise ones, over the signal. So basically, we take these things, and we want to actually be able to extract from that the kind of information. Each segment is basically, we're trying to do is we want to do this one derivative at a time. So the first order, second order, third order derivatives you saw, we want to be able to take each segment and minimize this. And we want to actually do this using L1, and we played around with L2 because we felt L1 was better because it actually tried to give us more information of a sparsity of the signal rather than just give the average. So the objective function of this kind of stuff was we want to minimize with weight 1 the first derivative, second derivative, and third derivative. And we also want to do this with sets of constraints. So this is basically, again, this time around, just to confuse you a little bit. Initially, I showed you plots going this way. I've turned it around a little bit. And so this is the maximum possible envelope of issues that we actually need to do. These could be constraints, and I want to find the best path within this envelope that meets all of those costs. I'm not going to go into a whole lot of details for this, but just to kind of point out some things here, we're just going to develop this quickly. And I'll show you more examples of this too. So here what we want to do is we want to find within this a region and be able to find the best possible frame to be able to compute this and find an optimal path that actually gets an update from the previous frame. I'm going to skip parts of this to kind of just say that basically it's about nothing else but looking for transformations from one viewpoint to the other and being able to account for residual motion computed over that frame. Now, I did say constraints, and all of this will kind of come back. So one of the things we want to do is we want to maintain a few bits of information about what's the scene about. Now, one thing I know, as I said, the assumption is the camera person, operator, has done the job of trying to keep the subject in the middle as much as possible. That gives us one hope, that at least the camera has some of that. But then the other things we want to kind of do is trying to add more information to make sure the main subject remains there. So that's why we actually did this whole approach of finding the best possible crop. So, top video is the original one. Oh, sorry, top video is the answer. Bottom is the original. And the red crop shows you the window as it moves around. Now, we wanted to do cropping rather than keep the same aspect and the size of the image, because otherwise this viewport would move away, and we would have to do things like in-painting. Right? Because if it moves out, I need to add more information. We didn't want to worry about that kind of, we actually played around with it, and it works fine, but in this case, the failure cases were much harder. We wanted to prevent, and we didn't want to do stitching to create a panorama and then find the best possible thing within it either. So here basically the idea was that we wanted to find this viewport moving around. We wanted to be able to keep some parts of rotations, affine motions, and also its translations within that viewport. So we want to also kind of point out that we wanted to prevent a lot of skew, because once it starts turning around on itself, it's going to have all kinds of other artifacts we don't want. And we want to keep it within certain bounds, and the bounds were really the original video frame itself. Again, we could actually play around with doing this L1 optimization as a linear program, and if you look at the paper, actually has the details of doing this kind of stuff, which is implemented exactly in there. But here, simply put, what we want to do is we want to minimize the three weights, W1, W2, and W3, at the three different types of the tripod, the fixed, the pan and dolly, and also the ease in and ease out. Of course, we can play around with these three different types of weights. Again, I've turned the axes a little bit differently here. Red would be the path if I just tried to optimize the tripod, a fixed one. If I start playing around and I give a weight of 1, 2, this is the kind of motion I would get. And the third one, when I actually just try to give it everything for parabolic motions, this is the path I would get. Of course, what we want to do is somewhere in the middle. And one of the things we could do is, since we now have a model of analyzing camera paths, is we can start learning approximately from data what those paths would be. And what we did was we actually observed a lot of videos, and from that actually kind of said this would be one of the set of parameters we want to use. And this is actually one of the numbers we have right now. This we have been adapting as we see more and more. And in fact, this gets to be an interesting side note I'll put in is we can actually learn specific types of things, how different movies do it also. So for example, not that I'm actually recommending anybody try to use our algorithm to watch Blair Witch Project or Cloverfield, you would actually see a lot more shakes in that one. But again, we want to try to stabilize this at causal videos, casual videos of this type. So we actually kind of play around with that set, and actually it's set into the algorithm now. So let's look at a few examples a little bit more. This is a video. As usual, we find our own family and friends to be our subjects. This is Matthias' wife, Sam. This is one of the first few videos we actually used for this project. From this, we can now find, and again, if you notice, there's a crop window bouncing around, and top is the answer. Now, for the real hardcore video people in there, you should be noticing there's a little bit of blur. That's a problem. We have fixes to it. I won't be talking about today. Another type of constraints is, again, we want to be able to find the most salient thing, because sometimes maybe that's not the case that the person who has actually spent time at it has found the right subject. And we can bring in other types of additional information from the videos to be able to help us do this. Of course, the most classic one is face detection, right? So run a face detector, assuming there's one face on the video. And we can give it two different types of things. In this one, we say, okay, we want to keep the saliency within this thing, within this region. This is without that constraint. So the face kind of moves around. But now if I just say add that constraint in, it's going to keep that video viewport within that set of constraints. And actually, these are rubber and so elastic constraints. They're not hardcore. So it'll kind of keep it. Of course, this adds to a little bit more blur. All right, so this afterwards basically resulted in this, and we kind of started testing around. And if you notice, this one had a huge, big jump in the middle. The top one did not. Again, a little cropped. And the other thing you will start noticing is the video length is getting longer and longer. This one actually is an interesting video, again, from the YouTube. Jumps there, but all of a sudden, the camera operator will do a zoom out. That comes to us for free. We didn't do anything with it. Of course, yes, the head did cut off. And again, as I said, if we had actually started accounting for, and this actually, none of these algorithms, this is actually running live. We don't do face detection on the live version at present. We actually started applying it to some of the very popular videos. This actually was a video that was getting a lot of hits on YouTube. Yeah, the head is cut off a little bit, but it doesn't have the jerky motion. Now, of course, one of the biggest things that offended users a lot was, how you're really cropping my video. And can you fix that? So actually, we have several algorithms to actually also fix some of that. We have to crop it a little bit, but not much. This actually should give you an example of an extremely hard case. For those of you, of course, who work in this area should know that snow actually doesn't really have a lot of features. But there are features, thankfully, up on the sky. And this is, I'll let this video keep going. It's a long video. Again, the top one is the running answer, and the bottom one is where you're showing that. Now, of course, the camera is really moving. When it fails, it moves back to the original footage as much as possible. And so the other thing to achieve this, and that's one of the reasons I'm showing this video, is we actually, and I'll talk a little bit about it, is we implemented this algorithm running entirely on a stream-based. So basically, we can run huge amounts of video. You can pipe in your 1-hour video. It'll run it on a stream. And that's why actually when I said 1, 2, 3, 4, what it basically does, it loads in the first 60 or 80 frames into the cluster to do the processing. Of course, after a few minutes, the next skier is coming down. You may have also noticed that the crop window has changed size throughout this video. So it initially was at 0.8, it moved up to 0.95. And again, these videos were not shot by us. They were actually publicly available on YouTube. Any person who works on this kind of stuff, and as I said, I have to really justify it to everybody, since I've written papers on it, that we've compared it to other algorithms. We're going to compare it to 3. First one is actually a paper that is actually Instagraph on 3D, where they actually compute the 3D model and do it maybe the right way, and actually has very good results, but it has problems of different type. Subspace video stabilization is the concurrent algorithm running right now in Adobe After Effects. That's widely used. It's even with educational discounts, is an expensive piece of software and actually has a lot of control. So it's much more for professional users. I think you will, after you play around with a lot of data, get quite good results. And last one we just compared, because everybody has the fact that, we can put more cameras on to something to look at scenes. So original video is the top one. Bottom one is our result, cropped a little bit, yes. This is comparison to the cropped version of the 3D video stabilizer that I talked about, to our result down below. Now, of course, after a while, this is going to get hard to start comparing, I understand. There are still differences. These are actually videos captured from better cameras, so you're not seeing things like rolling shutter artifact. We'll kind of resolve that as we go on further. This is when you actually do 3D video stabilization, so you've actually computed fundamental matrices and all stuff. Fails, boom, explodes. So ours is, in case it wasn't clear, I'm just finding a viewport. It's a 2D effort, right? Same video, compared again to the effort. They actually get a little bit more wobble, but I think they've better phase. Again, this is when we actually used their approach and downloaded it. Now it's become, they improve their algorithm, we improve our algorithm. So, but as I said, ours is a different kind of a beast. This is where the light field one. So this, what they basically took an array of cameras and figured out as the camera shakes which of the 9 cameras to use to give you a much more stable viewport. Ours is the answer here, comparison to theirs, where they actually figured out the best possible viewpoint. And again, comparatively, we do fine. Now let me actually quickly tell you about how we did some of the stuff to get it running on YouTube. And this is, again, stuff that Matthias did with a bunch of YouTube folks. And I already kind of told you the goals of this. To do this, first, of course, we had to take a video. And one of the bigger bottlenecks of trying to do this is we actually have to do motion estimation. This is not something that I'm going to claim runs on your laptop or on your handheld device in real time. It does take computation. So we actually had to kind of way of taking this video and dividing it up into a cluster. So if we take the video chunks, divide it up into a complete cluster of different types of servers. From this, the stabilizer was used to find the best path through all of the trajectories that are coming out, which was then used to do the cropping, and then live stream to the user. So when I basically, again, I'll show you many videos and I'll say 1, 2, 3, 4, 5, that's when it sends the whole thing to the cloud and computes the first bit, and then the rest of it's just following as we go. This stuff gets into a lot more how actually this is coming right out of the stream-based motion estimation work. There are versions of this that we have now at Georgia Tech that actually also use GPUs and stuff like that. So, and again, there's a lot of other work people have been doing on this kind of stuff. So I'm not gonna, say, but this is another example of like graceful failure. Because as you notice, this is a hard video, a lot of blur already in the original video. And look at the motions. It tries as best as possibly can to keep the camera stable up on top. This is the kind of the interface that's running. There are 3 or 4 different actually interfaces now. Initially, the interface was that you could hit this button stabilize, and you had a choice on how big of a crop window you want. So do you want the whole as close to the so actually we always limited to 95 to 75% of the crop. And you could play around with this. This is when it's being sent down to the streams. And again, you see the 2 views. Feedback came from YouTube saying people were getting confused on this. They didn't want to even have that bar. Well, a customer said that, so let's actually try to fix it. So we actually came up with approaches to automatically come up with ways of trying to optimize between a path. So we oops, sorry. That's what happens when you hit the button too fast. So we basically when a person was playing around with that slider to go from one cost function to the other, we basically figured out best possible paths through this. And again, I flipped this a little bit to optimize over this, but now we added other parameters over the weightage to be able to allow us to control that parameter also. So we optimized over this, and we learned again a little bit more about that parameter to help us estimate the window size. And you'll see this in this example here, crop 80. And based on the motion that it can stabilize, it's going to start popping it up. So this is also an automatic number now that builds it. Still, one of the things I'll tell you, one of the biggest people complain about is you crop my video. The other thing we did was basically create this whole stream-based approach, which actually is a predominant theme through a whole lot of our other work too that I'll talk about, is how do you take this whole chunk and create a small look ahead that overlaps with the other videos and use that as a constraint to run this as a stream-based processor. Actually, for those of you at ECCV, there was a paper on trying to do this kind of stuff for segmentation, which actually we've been running on a similar type of approach for a while. Let's actually see another thing. So this is actually something everybody asks me is, so hang on. There might be 2 different types of motions, a camera motion, but there might be foreground objects moving around. You want to be able to account for it. So of course, if the object in the foreground is small, we can detect that and account for that as not the dominant motion. Another thing that falls out of this is this allows us to, even with camera motions, find what I would call salient bits in an image. Interesting parts of an image even with a camera motion. And this actually allows us to do another interesting, and we have actually applied it to several different things. I'll show you one example of it. Is that like in videos like this, can I start looking for predominant motions that actually then I can start stabilizing on, or allow us to do better pan tilt or pan and scan. So wider video, I've kind of started cropping it, and I can zoom into things. So that original video had several motions, and you notice that we went from that, moved the camera and panned it based on the motion itself. So here you'll also see camera panning. Other people have done retargeting where they've tried to get rid of slices, and of course that compromises the original video. Here you notice the camera panned with her, and found the other subject, and starts moving around. So this allows us to really, so this is actually an output from a much wider angle shot. I'm showing you the result first. This is the original video. So here, of course, just because of the fact that we're modeling the camera, we can now move the camera where these quote-unquote at least the salient bits are. This one actually worked even better than I thought it would. Oh, I cut it off actually, when otherwise you actually see the character coming out from the other side.
So the retargeting part, in these kinds of videos, have you seen more camera motion? Because you're trying to reduce it on one end because of retargeting.
Remember, we can actually put in things which are the rubber lengths of how fast the camera motions would be. So we can control that too. So based on the saliency of the large dominant motion, as you saw the cars moving around, we can match it to that. So we synthesize the viewport to the conditions we want. So in this case, it will move from one to the other. Sometimes if there's a sudden motion, it'll do this. But if we actually, again, made that as a constraint where it does this, it's going to keep the maintenance of the kind of the pan and the ease in and ease out phenomena. Because that's always within our Elvin optimizer. So, sorry, question, yes?
Given that users don't like cropping, why aren't you using future information and past information to extend the image and then cropping that?
In this approach, we're not doing it, but that's the kind of stuff that's down the line, because we could actually create a panorama and find within that. One thing which we don't want to do, because that creates bits out of nowhere, is hole filling. And that actually has another set of problems where people said, okay, you're now making this appear. It only works well when there is like a lot of texture, but if there was a human face and you start doing hole filling, it's going to mess things up.
Well, but you also have to look at 3D there, right?
You have to look at 3D.
You can't just depend on...
You have to look at 3D.
Exactly. We are filling the holes when you're cutting my video, right? But actually, there wasn't the pixels there in the first place. The first pixels were in the head of the person watching.
That is another way of looking at it, exactly. I mean, there's a lot of stuff that was there on the periphery that we were actually not looking at anyways, but now all of a sudden ownership comes in and I want to see them more. But overall, I mean, I think most of the information is there. So now I'm going to switch a little bit and start getting into the fact that now we have these wonderful, cheap handheld cameras that have sensors that are cheap like hell, but everybody buys them for $100 with 2-year contracts. So this is the kind of, I mean, this actually is a real video from YouTube. This was an accident in Virginia. I think a plane crashed into a home. I mean, one of the other things I've gotten used to, I don't still understand why people take videos in this form factor, but people do. But you see a lot of shake going on, right? This is what we wanted to fix, and this was actually our answer. Take this video, and this is the output. Now, I don't know, I'm biased. I've been watching this video a lot, but it's a little bit more watchable, right? It's not perfect, because you will see a little bit of kind of the tree warping and wobbling a little bit.
As well as roll.
Yes, a little bit of roll too. It's not perfect, it's just better. Okay, so let me now go through and explain a little bit of how do we do this. But before I said this, let's take this example, earthquake. Now, actually, I'll be honest, this is actually easier than the previous one, because it's got a little bit of a rolling motion, which is perfect. This is, and people don't usually notice this is video, but now this is the output.
Was this intentional?
This was somebody just for demonstration purposes, yeah. Demonstration purposes purely. I mean, I don't think anybody does this, hopefully not, unless they want to make Blair Witch Project. So this is still video, by the way. All right, so here we wanted to now, and actually one of the biggest, crop was one thing that we got a lot of complaints about, but actually the bigger complaint we got was wobble and rolling shutter. So we started kind of saying, okay, let's fix that. And this was actually last year's work, and this was actually submitted to ICCP, and we were very pleased that they got the best paper award, and of course Srinivas's group got the second best paper award for that conference. So both the paper awards are right here, right? Yeah. So in this case, again, what we want to do, now of course I could do this on the camera again, but one thing I want to do this is I do not want to do it on the camera, I want to do it on the cloud. Now, one of the things that you may find interesting and surprising, whenever any video is uploaded, all metadata is moved away before they're coded up. There's no information, there is no standard whatsoever that even tells you that this video was captured on this camera. Maybe that'll change, but that's the name of the game. Photographs, people have figured it out. Metadata goes with the image. Transcoding gets rid of all stuff. So we want to do this without knowing anything about the video or the camera itself. We want to do it purely data-driven way. So what we came up with is a calibration-free approach and a mixture model of homographies I'll tell you a little bit about. What we did in this work also, and again, because we have to write papers and stuff, we did a complete user study to kind of see where things are. Now, people in this room are much more familiar, I'm assuming, with things like rolling shutters and stuff like that. A global shutter basically scans this way as video is captured, so it's much more faster and stuff like that, and kind of much more coherent. Rolling shutter is basically, as you kind of take videos, the sensor is also lagging behind, and scan lines follow a little bit slowly. The artifact is that's why you saw the wobble in the image, within the constraints of the image itself. And that's what results in videos like this. This is the original video from actually one of the leading papers on rolling shutter removal. You can kind of see the warping going on. So this is the original video. Really hard video and bad quality too. Initially, when we just applied our previous approach, without rolling shutter, this is the output. Now there's another problem that people will notice is, if you notice that input text because of cropping is getting more annoying than even anything else. Another thing I don't understand is why do people put labels, but we'll worry about that later. So what we wanted to do was fix this. So how we basically did this was we wanted to actually model how the global versus the rolling shutter model varies with scan lines, and how do we kind of model all of this. So this is basically just approximately looking at it. As you scan one frame, this is the first frame, the second frame, the third frame, things have moved around, but luckily, we hope that the scan lines are still dependent on the hardware itself, and they will be same for the same camera. So to achieve this, I would actually look at this, and to model how X has moved to Y from one frame to the other, I would be able to invert the information in a global model where there would be no translation to get where my X and the Y relationship was. In rolling shutter, I would also have to account for the shift because of the fact that the shutter has kind of moved over time. So this, of course, is fine. Of course, what we want to do is we want to be able to model this as a parametric motion model. To do this, we basically rewrite the equations and actually account for these types of things, the same shifts in X and Y, or from X to Y. And we're actually now basically look at homographies for these types of things, which basically now allows us to take this signal, break it up into two chunks, and create homographies for those types of things, and basically put Gaussian mixtures between them. So allowing for those Gaussian mixtures, we actually almost kind of, I'm going to use the word learning, it's not learning the parametric model of those two different types of slides of regions moving over. Again, we wanted to be doing this from the data itself. And then we come up with a whole types of ways, including iterative recursive least squares methods to be able to kind of look at this stuff. Again, taking these kinds of videos, we account for variations in this, and this is the original video. Final video, with the homography mixtures being used. There's still a little bit of wobble, but well, we think it was better. So what we did, and I'm going to skip over this parts again. These were just in case we decided to get into this kind of stuff. What we did was also did a small user study. What we did was we basically popped up a website, populated it, and put three: original, method A, method B. Of course, we didn't always say which one was ours, method A or B. We kind of kept on shifting it. And we did this kind of studies. Of course, in this one, I'm showing you the labels. In that case, we didn't. So original, Baker et al., and this is our approach. So a couple of times, the cropping and stuff is different. And this was done, as I said, we did it over this. The bottom line, and I wouldn't be showing this to you, would I, if we had not done well. The red one is ours, and we did well. So most of the time, for a whole variety of video data, we got better results on the user's test. Now, of course, were these users, most probably best selected sample set or not, but I kind of say jokingly that it was good enough to get our paper accepted. Now, of course, as we put this out, all of a sudden we started getting a lot of interesting examples. So this is another example. This is actually a riot in Syria. Original there. And this one is, actually I should have put a label on it. This is the output. See the building shake? It shakes less. I'm not officially going to claim doesn't shake at all. Oh, this riot is about to go to hell, let's move away. This is the same video I had shown earlier. Still a little bit of shake, still a little bit of roll, but, and actually you'll notice it, watch the pillar. I mean, the telephone pole warps out a little bit more. So as soon as you see a little bit of thing, the telephone pole does do a little bit. They're there.
Would be good if we could enforce perspective projection on your output, right?
So we're doing that now too. In fact, that version is actually, this is an older video. Actually, if you run the video on the YouTube stabilizer now, it does that too. So we actually account for that a little bit.
So that's a baby step towards full 3D modeling. And you have noticed if you've done that when we're looking at people in the foreground, their heads bob up and down in a very unnatural way. Are you going to go to full 3D modeling?
I don't know how to answer that question without getting myself in trouble.
Okay.
You got the answer though, didn't you? Yeah. Okay. So yeah, another, this is again running live on this kind of stuff. I mean, the fun part of it is, in fact, just today I went to it. This is when you actually have a complicated world that they keep changing the UI and everything around on you. So just today I went there, the UI was different. But that's the kind of stuff the YouTube tube is doing. We're not part of that anymore. And this work was entirely done at Google. Again, you know, a series of other examples at the same time. Press one button, 1, 2, 3, 4. Stabilized video. Oh, actually, the real-time preview is about 1/4 video resolution. For those of you interested, after you do this thing, there is in the UI, there is an option to save your MP4 file back. And you can actually do this keeping it private too. So many people come and tell me, I don't want to upload my video. Now, yeah, you upload it, you keep it private. This is being recorded, I can't say other things, sorry. But, you know, but you can save this entirely and delete it from the web page if you want to. And more examples and stuff like that. So bottom line is we showed you a unified framework for doing stabilization and retargeting because it allows you to do this pan, tilt, and, pan and scan. Calibration free completely, so it doesn't know anything about the camera or any set of parameters, stuff like that. That calibration free part, actually we're applying it to other bunch of different things too now. Learning, brightness, dynamic range, and all that kind of stuff too. And the rest of it I think I've kind of hit on. Let me now show you a little bit of bonus material. I'm trying to now say that one of the other things we've been working on is trying to actually also do the low-level analysis of videos and extract from that more content from video. And more interestingly, this is the lower level information like regions and video segments from video. So here is an example of a video that could be out there, and I want to be able to, from this one, be able to find interesting patches and regions. I load a segmentation algorithm which finds all these super pixels over time, super voxels, and now I can go in and find regions that I want to actually highlight. So just by one click, 2 clicks, and stuff like that, I found 3 different regions, and now I can, this is not very accurate tracking, but these are still regions that we can observe over time. The reason I'm actually showing this as a motivation part is one of our goals, and we have a version of it, we haven't released it, is we have a web-based, flash-based complete tool to be able to do this and save a JSON file of complete regions in a video, in a temporal pattern, temporal video sequences, and also the original segmented regions for other processing. So we're working on that kind of stuff, but this is actually one of the things that we're running into a little bit of problem is releasing this kind of stuff. This is basically the idea behind this work is that if you have videos like this, and this is again what we love to play around with, videos that are hard, and if you were to run just simple image-based segmentation on it, you will lose out on things like temporal consistency. Now, we could have been a little bit more intelligent and kept certain regions to have the same color IDs as we go from one frame to the other, but we want to be able to not only just do that, we also want to find best hierarchies, that is, best regions at both under segmentation and over segmentation, and find a path to be able to allow us to find these super voxels over time. I'm skipping over this kind of stuff. So, this is something we can also kind of look at. This is a very famous, of course, flower garden sequence. We can actually do over-segmentation on this kind of stuff, which is based purely on appearance models and stuff, but of course you see a lot of different types of things happening. We can add optical flow in there, and you can see, consistent regions move around, and this is something which we are actually now working on towards trying to get depth layered images and stuff like that. By the way, this stuff is actually both done at Georgia Tech and at Google, and a lot of other stuff at Google is using this video-based stuff also. I'm going to skip over this stuff too. Sometimes I forget some of my slides have animations. This is, again, basically being able to look for connected pixels. All of the approaches and stuff. Again, the same kind of stuff I said before. We basically do it as a stream clip-based processing. We take a region, take a part of it into memory, process it, and then find another part, and basically use that as a constraint graph to go from one to the other. And this allows us to do things which are basically shown here. And oh God, this slide is going to take ages. I just added this in just before the talk, my mistake. This is going to take ages. Let's get out of this one. Oh, don't do this. Oh, I decided to save. Okay, so let's show you the results. So this is the original video. Take the same appearance and bit of motion, and we can actually get an over-segmented sequence like this. Now what we're going to do is, as I said, we're going to keep a hierarchy of over-segmentation down and move it to under-segmentation through a set of hierarchies. So here I can go from full over-segmentation and start kind of going to another hierarchy, 5, from 5 to 10. And from there, actually, this is where some of the best results are coming in. Now, of course, here you can see much better. He's one person and all that kind of stuff. The pillar is one. There is, it's just, it kind of breaks apart. But the explosion is also kind of visible, but is a mixture of things. One thing we haven't done in this one is figuring out which is the best hierarchy to do the analysis at. We present you with all of them. So one of the bigger questions, anybody wants to work on this, I'm happy to collaborate on it. We have some ideas we're working on also, is to figure out based on signal and the strength of the signal and local support, which hierarchy and how to use the clustering of objects. As I said, I am working on trying to use this for layers, which hopefully you will see published sometime soon. This allows us to, as I said, be able to really kind of start segmenting regions. And actually, some of this work is now actually being used for doing things like activity recognition and action recognition also in my group and other groups too. This is the kind of output comes from this. So here, if you notice, it's actually a relatively hard video. Water is always a problem for any kind of visual analysis. But here, of course, he's wearing the right black clothes, which helps. But you can see even with him doing whatever, 360, 720, there's still one region around the clothes. Next one is actually another interesting example. Again, you can see really dark images and stuff like that, but still being able to move and being able to crack those types of regions over time. This is actually one of my classic favorite examples because I find it amazing personally that you can still see this guy down there. You can't see his surfboard though because it does gonna get mixed up with the water a little bit. And using this, and I kind of already showed this, this becomes nice an interface to kind of be able to do things like just on one click finds and tracks Kim while she's doing ice skating. Of course, when she comes up here, you'll see the hair is black. It's appearance-based, color-based model. It does mix up with the citizen thing and loses it. This is actually a UI where I can go back and click on it, and then it'll propagate both backward and forward on this kind of stuff. But this is, again, as I said, we're just playing around with these types of things to kind of show that this can be done. Everybody who sees this asks, oh, you could have just done motion differencing. Well, this is the output of motion differencing. The thing it is, with ice in the background, there's a lot of specularities and reflections which make it harder. Of course, what kills us in this is the blocking artifacts of MPEG coding does affect us. So you kind of see his head not being segmented very well, and you can actually see the blocking artifacts. So it's work in progress. What we've done for this is, and this is actually an older version too. If anybody's interested, go to videosegmentation.com. You can upload your own videos. and get, at present, a JSON which has all of the regions in a kind of a markup language. We also provide you with a kind of a file handle to be able to parse the JSON thing, and also lets you have the videos and stuff. Unfortunately, if you upload a video that's like 5 hours long, or even actually 20 minutes long, we might kind of push you back and saying hard servers cannot support it. If anybody is interested in writing a huge grant with me to get this kind of project funded, please apply with me, because that's the kind of stuff we would love to do. Is I'd like to make this as a web API available on a cluster for anybody else to be able to use and extract these kinds of features as much as possible. And as I said, this has been running for a while now. Many people have been using it. So this one, again, very quickly, I just kind of said is it's a hierarchical segmentation approach. We don't really worry about features. And in this case, for the lower-level stuff, we use color, texture, motion. Actually, there's a newer version that also you can attach a connect to it and get RGBD for segmentation and improve the quality of stuff like this. It's purely clip-based, again, like the previous approaches. That is, that it gives it streams, and it keeps processing as it moves forward. We've actually added to it that it basically does it within memory. And actually, there's a newer version that I have on the next slide, but maybe I won't show, that we actually have it optimized to run in real time on a decent laptop. And one of the reasons we wanted to do this was, and you can imagine why I did RGB and D and stuff like that, we want to start putting this kind of a pre-processing step on robots to be able to see the scenes and stuff. So this is one of the real-time versions and stuff that runs. We are also, as I said, this is the annotator that we're working on that we hope to release sometime soon. And as I said, all of this is coming. With that, I am going to, this is basically the annotator that lets you kind of play around. It's completely flash-based. You see the regions, you can paint parts of it, and then be able to kind of save things off. Because one of the things we want to do, and this is again trying to copy the whole, that everybody's doing a lot of great work on annotating images and stuff like that. And people have done stuff on video labeling too. We want to get it down to the region levels and stuff like that. All right, with that, I'm just going to stop and take questions for anybody. I went through a lot of stuff fast. As I said, all of this is running. These are just some of the highlights. Actually, the interface that the YouTube people did is amazing. You can see this right now. That is, you can go from seeing the original to the stabilized one. This is cute. I mean, this is, I showed you this videos before, and you'll actually kind of see, this is our first version of doing the stabilizer. Didn't work very well for things. This is with rolling shutter removed. You saw some of these videos. Now, of course, I think you said, this one, we're really shaking it. I mean, earthquake mode is what I call it. But it works well, and you saw this video too. And again, anybody interested in both graduate work at Georgia Tech, postdocs, or people want to apply for faculty positions at Georgia Tech, we have lots of vision, robotics, graphics, HCI people, and we're looking for good, smart people to join us. Thank you. Takeo raised his hand. I have to answer Takeo first.
Applying a faculty position.
Shh, nobody heard that.
2 questions. Rolling shutter things. The fact that human thinks that this is wrong must be coming some, I think, knowledge or assumption, whatever you call, not the physical reason.
Rolling shutter or cropping?
Rolling shutter. So when you see this is, people say this is better, this is worse. Or even I said, still this bending.
Yeah, okay.
You and I feel the same way.
Sure.
Is that, that is only coming from this meaningful thing like, oh, this is building, therefore it should not bend. This is the pole, which of course if it's earthquake may be swinging, or if it's a road, it may be waving because of the earthquake. Somehow we have a come up some reason. Is that only?
So our experiment we did, and even looking at most of the data that we have done, I mean, it's not the most quote-unquote scientific, but it's really looking for is asking the simple question, globally, which one is looking better? So globally, basically, this one is shaking a lot, as opposed to one tree kind of wobbling a little bit. At least in this experiment, people kind of said is, I can forget that tree wobbling a little bit, because this one I cannot watch. Now again, as I said, if I had used, I don't know if you've seen these movies, Blair Witch Project, and people are intentionally doing this. That's the goal of the designer. Maybe in that case, somebody should have given them the context that this is better, because somebody spent time. If it was an earthquake video, it would have been better. Actually, I didn't show it, when the tsunami hit, fortunately part of Asia, there were lots of videos uploaded with shakiness, all that kind of stuff. Of course, most of it was because everybody was shaking and stuff like that. And it actually did try to smooth that out, which actually was a wrong answer, right? Because it attempted to do what it could. It's a purely data-driven approach. So it does, and in fact, we've even done things like analyzed videos from Blair Witch Project, and it actually does try to smooth it out. Artistically and visually, that's the wrong answer. So I'm basically waving my hands on this one is because we're trying to smooth over an optimal function and finding an optimal answer. Is it the right answer? Depends on the user.
One other short question. The video segmentation, that is segmenting by using the whole sequence.
No, it basically starts off with about 30 frames and about 20 frames on top, runs it and overlaps this on the time. So it's not a batch process.
Context requires about 20 frames.
Yeah.
What is the shortest?
At present, 20 is the shortest that we have played around
You
with.
make it shorter, then it doesn't do as good.
Actually, we have played around with how to play with that number too. And basically that has allowed, because one of the things, in fact, I have another project which actually uses a handheld camera and does initial segmentation on handheld and streams the rest on the video. So we've played around with moving that window a little bit. I have nothing to report on it yet, but we're playing around with that kind of stuff too. We're doing kind of the course to find between the cloud and the local server. I mean, that was one of the reasons we're building this cloud-based thing, is because we want to actually, I have another series of work that's going on entirely on doing a whole lot of this stuff on handheld cameras right now.
The shorter that region is, the value of that program for real-time application will increase tremendously.
So, but that's why, as I said, but basically we want to take a little bit of the stream and process it, and then you update it by 5 frames after that. So we actually want to just keep about 20 or 30 frames in memory, and then we can actually do it. For the stabilizer, we do about 80 frames, and then the rest is 20 frames on top. So we've been playing around with a lot of different approaches for stream-based processing, where only the update information is a small window. Yes, Alyosha.
So, not that I am against all the data-driven stuff. But
Really?
That's perfectly fine. But I was wondering, the whole idea of an intent, is maybe there is something physics-based that you can say about the type of motion or the type of acceleration that happens when you're holding a small object with one hand, and basically look at maybe the typical frequencies and pick those out and not.
So actually, as far as I know, based on published information, a lot of the handheld cameras are now doing that. They're using the IMU as a predictive filter to get rid of a lot of the high frequency and low frequency motions. Okay. And actually it's hard to do this for rolling shutter directly, because we don't exactly know how the shutter opens, but actually by definition those cameras know the model of how the rolling shutter works. So there is a lot of this stuff is actually now happening, and in fact, can't talk about, there's some other stuff going to happen soon, which is going to do both local and global local and cloud-based processing. Androids are going to do this, and so is iOS.
But I guess I was thinking of in your pipeline, even though something might be gotten rid of, there's still some of that information, and basically all that you want to decide is what is the shape that you want to keep. The artistic shape versus the non-artistic shape. And it might be that just looking at the frequencies.
I couldn't agree with you more. Exactly that's the way we want to go with this kind of stuff. And we are. And in fact, as I said, the funny things, if you really look at professional videographers, a lot of them are actually putting encoders right onto the cameras to actually capture that additional information for various purposes. Now, of course, usually it's to figure out camera paths and stuff like that. In our case also is we want to actually model those camera paths without any information. One of the beautiful things that we learned afterwards was, this can be actually applied to any video and that's one of the beauties of it. But if you come up with additional metadata in the front end, we can improve the quality by this approach. I mean, again, as I said, this might be scary to you. I was telling, I think Marshall today, I don't know who was talking to somebody this morning, Fernando, that I don't know if you guys know, for some unknown reason, and this is being recorded, I don't actually speak for Google, by the way, this is just my individual thing. Every minute, how many hours of video is being uploaded to YouTube? Any guesses? 72. 48 was last year. 72 hours of video are being uploaded to uploaded to YouTube right now. And there is other sources that actually are getting a whole lot of this stuff. Now I know most of it is cats, dogs, and stuff like that. But,
what this means is that nobody's actually watching this. Most of those pixels never see the light of day. Yes.
Actually, there are interesting statistics on that kind of stuff too.
So the decision to stabilize or not, that's made by the person uploading, not the viewer, is that correct?
No, actually, there is another part of it that I did not get into is we have actually learned what a shaky video looks like from data. And so basically, when you upload a video, it pops up a banner saying, by the way, we've noticed your video is shaky. Would you like to fix it? And there's one button, yes or no. And you'd be surprised at the number of people that are saying yes, even for actually pretty decent intentional videos, but they still kind of, and it improves it. I mean, it does stabilize it and stuff like that. Then it shows you both versions, the preview version, and then you say save this or not. So we detect it on upload now. And so it lets you do, I mean, that's one of the reasons actually I can't tell you the official numbers, but you can imagine this software has been used by many millions, is actually getting quite a wide usage. Now, of course, you can always go to Premiere and do it much more professionally. Yes, Chris?
So, I'm wondering about the role of semantics. You did see places in your first thing, but then after that, you totally rejected semantics. What you're looking at. This is in some sense a parallel question to Alios's question. You know, most of the time there's people in the picture. And by seeing people, you do a better job segmenting and all this other stuff. So why this know-nothingism?
It's actually not known. I mean, you've known me for a long time, Chris. I mean, you know I come from that end of the world. And so I'm trying to reach both ends, trying to get in the middle again from the other side. So we're trying to now get to the low-level bits of information and trying to also not forget that there is a lot of high-level information, people, tracks, and stuff. So I did say there are 3 threads to my research. One was the low-level video analysis and enhancement. I did not talk about the middle layer, which was basically doing behavior and activity recognition, which is purely driven on finding where people are, what they're doing, and also actually predicting what they're about to do. And that is pretty much actually almost 1/3 of my research effort. The one good thing is now actually, one of my frustrations has been in a while is that the features we've been using for video analysis are still over 2 frames. I mean, they're very simple local features of edges and stuff like that over very local neighborhoods. The question now is, can we actually extend the video volume and find features that actually are going across it? And now this kind of stuff that actually we can do with segmentation, and actually the stuff I kind of touched on with saliency over time, is allowing us to come up with these very nice features that now actually we are working on to try to get back to it, and adding things like higher level things like where people are. And so actually, and interestingly, we can actually make this now work on handheld cameras as you move around. And in fact, I hope to have that kind of stuff to show you in about a year. I hope I haven't released, I mean, this is all Georgia Tech work, and you know, I'm trying to hope that if you review it, you like it, please accept it. Anything else?
Okay. Well,
thank you so much.